So MOSFET is one of the basic building block of this modern integrated circuits. So your integrated circuit is made up of millions of transistors, and so one transistor, how it looks like and what is the operation. So we will look at that, and particularly we will emphasize on the role of materials in deciding the properties of the device. So here, so MOSFET, like last time I already mentioned, so MOSFET stands for metal oxide semiconductor, and FET stands for field effect transistor. So on the left hand side, you see a picture of NMOS, so which means you can say it's a N channel MOS. So similarly, PMOS means it's a P channel or a whole channel MOS. That means whole is the primary or a majority charge carrier in this device. In NMOS, it will be electron. So the device is basically you have a block of semiconductor. So let's say P-type semiconductor. So you have a P-type semiconductor, and then you dope heavily with N-type material and make two regions which are known as source and drain, S and D. So you call it a source and drain. And basically what during the device operation, what you expect that there is a flow of electron from the source to the drain. Okay, so there is flow of electron when the device is on, and this, how will you switch it on? So for that you need this gate. So gate, as the name suggests, it's like a gate which, or a door which allows when the electron will flow or when the electron flow will stop. So this gate is normally a metal, but in case of a silicon a MOSFET device, so this gate is a not a normal metal. It is made up of this polysilicon, which is a polycrystalline silicon, and basically it's a degenerate semiconductor, so which is heavily doped and behaves like a metal. And then between your metal gate and your P-type semiconductor, this white region is the oxide layer. So this is the oxide layer, which is not conducting, it is an insulator. Okay, so oxide is basically the insulating layer. So sometimes this MOSFET, if instead of if you don't use a oxide layer, so it will be called a metal insulator semiconductor, MISFET. Okay, but most of the this devices, transistors are where oxide is used as an insulating material, and that's why the name is metal oxide semiconductor field effect transistor. And this oxide layer is, in this case, if you take a silicon, so the oxide layer will be again say silicon dioxide. Okay, so this is the dielectric or the oxide layer that is used, which acts like a barrier that electrons, so in a way electrons cannot flow perpendicular to this in this direction. Okay, so electron flow will only happen across this from source to drain. So there is no flow of electron perpendicular to this interface. Okay, so it flows only from the source to drain through this a channel which forms underneath your oxide layer. So this is so the P-type will be exactly the same. Only thing, the N and P will be inversed, and other things remain exactly the same. And here the channel where your charge carrier flows, it's actually the hole that will actually flow through the channel. So again, this is the same picture. I will show you later how the circuit diagram looks like, and then we will see the characteristic of behavior of this transistor. So you have basically again a source S, drain D, and you need to apply a voltage to the gate. So what we want to have a current from source to the drain. So that means we need a conducting channel through which electrons can flow from source to drain. And that is possible when you apply a certain voltage to the gate. So gate is acting like a switch. Okay, so when the gate voltage is above certain threshold voltage, so then only the channel will open, and then electrons will flow from source to drain. So what is most important in this device, that you need to apply a gate voltage, so which if you want to switch it on, so it has to be more than a threshold voltage, which is so depending on device, this voltage, threshold voltage, can vary, but it is typically of the order of like 3 to 4 volt. So it can vary, but basically it is few volt. Okay, so this is the voltage that you need to apply to gate, so that you can create a channel, a conducting channel underneath this oxide layer. So this is your oxide layer here. So you create the channel which connects the source to the drain and leads to a flow of charge carriers. So this current, the flow, a current from source to drain, we call ID. Okay, this is known as ID, the current from source to drain, which will be a function of the gate voltage, as well as again you need to also apply a voltage across the source and drain. So that is also so the ID, this current, will also depend on that. So let's look at the circuit diagram first, and then we can understand the characteristic of the transistor. So basically what you do is, so you have the gate and the source, so they will be connected like this. So this is your VGS. So this gate voltage you are applying is between your source and the gate, and then you apply another voltage here. You have drain to source or source to drain, VDS. So this is voltage you are applying between source and drain, and you also need to connect your source to the back plate of the substrate, so that they are all in the same potential, so there is no flow of electron across the device. Okay, so you are applying a voltage VGS between source and gate, S and G. Then you are applying a voltage between your source and drain. So remember, so your drain is connected to the positive terminal, your gate here is also connected to the positive terminal. But in case of a P-type PMOS, so this will be reversed. Now let's look at different situations. So the first situation is that your VGS is less than the threshold voltage. So threshold voltage is a voltage which is normally fixed for a particular device, and when we say your gate voltage is below threshold voltage, your ID, this drain current ID, will be equal to 0. So because there is no, so when you look at the device, so you have a N plus region or N type, then you have a N type drain and a P type. So then immediately you will have a depletion layer, right? So this is your depletion layer that will form uh, similar to your PN junction, like your diode. So you have the depletion region. So that means there is no channel has been formed between the source and the drain. And this happens when the device is you fabricate the device. Now, if you are applying a small voltage across the source to gate, so which is, let's say, less than your threshold voltage, the current ID will be always equal to 0. So you say the device is off. So this is your off state. Okay. So ID is equal to 0. So whatever you can increase the VDS, but still your ID will be always, the drain source to drain current will be 0. So that means if I plot ID versus VDS below this the threshold voltage, so there will be no current. It will be basically 0. There will be no current. Sorry. So there will be no current. It will be always 0. So ID is equal to 0. So this is your device is in off state. Now you increase your gate to source voltage. So now I will draw the circuit so that it will easy to understand. So now, so let's go to this page here. So now let's say I increase the gate voltage and make it greater than the threshold voltage. So what would happen in that case? So I have the device here. So this is my N channel, source and drain. This is, I have the insulator here and then the gate. Okay. So this is my source, this is my drain, and this is my bulk P type. So we are talking about the NMOS device. So the connection is again the same. Everything remains the same. This is, you're connected to the positive terminal. Okay, so this is your VDS, this is your VGS, and this is again connected to your bottom of the P type. So now when your gate voltage is greater than threshold voltage, in that case what happens, there will be a channel that will form between your source and drain. So just underneath your gate, insulating gate. So you have the gate and then the insulator just underneath that. So there will be a, is known as a inversion will take place. Inversion layer, and that will connect between your source and drain. So a N channel has formed when the gate voltage is greater than the threshold voltage. So N channel has formed. That means you have basically free electrons which can move now from source to drain. So that means your ID is not equal to 0 anymore. Okay. So this is your on state. So device is an on. So, and what happens to the depletion region around your source and p-type? So this remains the same. So your depletion region will still be there. Okay. So this is not going to change. Only thing what has happened, that a channel has formed between source to drain, which allows the flow of, so it is now becomes a pure n-type material below the your oxide layer, starting from source to drain. And that means there is a flow of current ID. So you will have a flow of current ID which is not equal to 0. So now if you want to plot that, so now you increase the VDS and measure a plot what is ID. So again it will increase almost linearly. So and what is ID? ID will be equal to your voltage that you have applied divided by resistance of the arc channel. So it is simple, very becomes something like a your linear dependence. So you have established a pure n-type material simply by applying a voltage on gate. So you, that means in the p-type region, so you have a p-type region, but now this p-type region is devoid of holes, and there may be acceptor ions, but still you can create a inversion channel or an n channel where you can have a flow of electron from source to drain. So similarly in a PMOS you will have a flow of hole from source to drain. Now what happens if I keep on increasing the this VDS? So will it just keep on increasing like linearly? No, it is not. So what would happen to the channel in that case? So let's look at that. So now we have established that we are above the threshold voltage. So the gate voltage is above threshold voltage. So that means we have opened up a channel and we have some drain current. So typically this drain current will be in the range of, it should be in milliamp range. So voltage, we are always, all of this voltage that we are talking about in few volts. Okay, so either maybe 3-4 volts or 5 volts or 10 volts, something like that. And now if I increase the VDS further, so what would happen? So let's look at 2 points here. So this is one point, let's say call it point A, and this is another point here, point B. Okay, so they are very close to the boundary between your, or almost close to the depletion region. So this point. Okay, so what would happen? What is the voltage at point A, or the voltage drop across A? So voltage drop across A is, so let's say, so let's say voltage drop across A is, point A is always VGS, right? Because it is again between your source and the gate, so the voltage drop will be always VGS. That remains always constant. Once you are above the threshold voltage, so this VGS is not changing. Now what is the voltage drop across point B? So across point B, which is close to the drain side, so that voltage will be VGS minus VDS. Okay, so this is the which we call as VGD. So this is the voltage drop across gate and the drain. So VGD, which is, it will be equal to the voltage drop across VGS minus VDS, or VDS minus VGS. Okay, so something like that. So this is the voltage drop across B. So that means the voltage drop across point A and point B are different. Now if I increase the voltage VDS, Okay, so I am not changing the voltage drop across point A, so it is always VDS, but I am changing the voltage drop across point B, because if I am increasing this VDS, so VGD will change. So what it means? It means that you will have a situation if you further increase the drain to source voltage. So it is possible that your channel will then become narrower on the drain side. So there will be no effect on the channel on the source side or at point A, but the channel width will change on the B side, because the voltage is changing, or that means the electric field is changing. So this channel will, the width will change. And what normally, if you look at it, so it is actually in a reverse bias condition when you increase the VDS. And what happens is, so let me draw that again, so then the things will be clear. Sorry, let me put that. So I have again the situation here. So let's say I have the N type. I have the gate here, insulator, and then the gate. And so now I connect this to this. This is again VDS. This is VGS, and this is connected to your P type. So what happens now if I now VDS is increasing? So channel has been established, but now if I increase the VDS, so the channel will remain the same. There is no change in the channel on source side. But on the drain side, so again, I will have a increase in the depletion layer. The depletion width will increase, and at certain VDS, so there will be almost, it will be like a, the channel will narrow down and it will close actually. So this is your depletion layer. So the width of the depletion layer will increase, and it will actually close the channel or narrow the channel. So what happens in narrowing of channel? And this situation, when it just at the voltage, the VDS, where the channel will be just closed, so that is known as pinch off. So you have a situation which is called as a pinch off. So what would happen in that case? Your current, so current will then saturate. Okay, so if you plot now your VDS as a function of or drain current as a function of VDS. So in the beginning it was increasing, but when you reach this pinch off, so it will get saturated. Okay, so somewhere this is your VD, so this will correspond to VDS saturation. Okay, and this is your IDS. So drain current will also saturate, and beyond this VDS, now if you further increase VDS beyond this pinch off, so here what you have is a pinch off. So if you increase beyond pinch off, the voltage, if you increase further, so what would happen? So in that case, the depletion region will basically, the width of the depletion region will increase. So again, if I draw like this, so the channel on the source side will remain the same, but the point where the the channel now cuts or doesn't connect anymore to the drain will increase basically. So let's say this is my drain. So basically what is happening, your depletion region width will increase on the drain side, and you have basically so there will be a current, saturation current, which will flow through the channel, but it will not anymore increase. The current will not anymore increase, it will saturate. Okay. And the extra voltage that you have increased beyond VDS, like if you increase beyond VDS, so whatever voltage that you are applying will actually drop across the resistance in the depletion region. So this depletion region has its own resistance at a higher resistance. So most of the voltage that you increase will drop across this depletion region, and your current will not increase anymore. So IDS will, so the drain current will saturate, which is given by IDS. Okay. So this is a characteristic of a MOSFET device. So let me, if I plot this ID versus VDS for different gate voltage. So we have three parameters. Okay. So we are applying a gate voltage. So gate voltage is basically acting like a switch to turn the device on or off. So if I plot this ID as a function of VDS, so when VGS is less than threshold voltage, so let me take this. So this is my, when VGS is less than VTH, so ID will be 0. Now just at when VGS will be equal to VTH, so you'll have probably a very small current from source to drain. So the channel just opens. So this is when VGS is equal to the threshold voltage. Now if I increase VGS, the gate voltage, further more than the VTH, so I will have something like this. Now if I have increased the gate voltage further, so something like this, it will look like this. So you will have, this is VGS 1, let's say this is VGS 2. So where I'm increasing the gate voltage. Okay. And the saturation, this is your IDS 2, this is your IDS 1, and so on. So this is how the characteristic would look like for a MOSFET transistor device. Okay, so you have a control voltage, your gate voltage, which is controlling the device to make it on or off. And then also you can, it is also, or in a way, so there are two functions which we are looking at. So one function is, so there are two functions this transistor is doing. So one is it is like a, so switching on or off depending on VGS. Okay, so this is like switching on means you can say this is a 1 state, and off means is a 0 state. Okay, so this is, then you can perform these logic operations using this device. Okay, so another thing which it's also doing is amplification is also possible like a normal transistor. How? Now if you increase VGS, so you can increase the, for the same, so if I am at the same, let's say this is the VDS I'm applying. Okay, so let's go back to this here. So this is my VDS. For the same VDS, now if I am increasing the gate voltage VGS, so I can increase the saturation current. Okay, so that means I can actually get a amplification of the signal, and this acts like an amplifier here. Okay, so for the same drain to source voltage, depending on what is the gate voltage, I can get more drain current. So it is also performing a amplification as well. Now if you plot this saturation current, you can also plot the saturation current as a function of the G here, and we see how the amplification works. So now is almost, the curve would be looking like this, where this is your threshold. So below threshold there is no saturation current, but if you increase the VG, so you can get a amplification and higher drain to source current. So your transistor is performing two functions. So one is, it is acting like a switch, so you can perform logic operations 1 0, and it is also acting like an amplifier as well. So that's why this MOSFET device became so useful and used in most of the integrated circuits. Now let's look at like how the material leads to, or what is the role of the material here. So to understand that, so I will just write down the relation between your drain to saturation current, this drain current, the saturation current IDS, and normally the behavior you can write minus VTH square. So it's a parabolic dependence, and sometimes we have to actually add for some a small dependence on VDS. So but normally it is negligible. This term is not that important in determining the current from source to the saturation current. But most important is this VGS minus VTH square. So it is parabolic dependence, and the K is a constant which is given by this relation 2L box. So let me describe what are all these terms are. So Z is your width of the gate, L is length of a gate. So basically it is also your channel length. These are like this Z and L depend on the how small you want to make your device. So sometimes you cannot compromise too much, because if you change this Z and L a lot, so the fabrication process can go wrong. So these parameters are normally not so to say affected or varied so much during the fabrication process. But there also, this is a geometric dependence. So they are not a material dependent property. So they are more on geometric dependent. So Z and L you can understand from this picture here. Yeah. So Z would be the width of the gate. So this is your, let's say this is one is Z, and the other one will be your L. Okay, so this is again a geometric dependence. Okay, so there is no material dependent here, but other terms depend on what kind of material one is using. So let's look at those. So T ox is your thickness of the oxide layer. Okay. So why we are discussing these parameters? Because we want to make sure that, so if you look at this K, the constant, so the dependence. So now if I decrease the oxide layer thickness, I can increase the IDS. So if I want to increase IDS, so I want to increase the K value, or the constant, right? And to increase this K value, so I have to decrease the, if I decrease T ox, the thickness of the oxide layer, so I can increase K value. So one way of increasing this drain to saturation, or the saturation drain current, is by decreasing the thickness of the oxide. So if you decrease the thickness, so you can get higher drain current for the same device. Okay. But there is also a challenge in the fabrication, because this is you need to, so typically let's say the thickness would be around, let's say 100 nanometer. Okay, so such a thin insulating layer, depositing it on top of your P-type semiconductor or N-type semiconductor is a challenge, and you have to make sure that it is really smooth and there is no roughness at the interface. So this is a challenge in the fabrication process. So uh, in industry, they do use this trick to reduce the thickness so that they can improve the device drain current. This is one way you can control that. Another two parameters are mu E and epsilon. So let's look at epsilon, or this permittivity. This is permittivity of the material. What you want is, you want to increase the permittivity. So if you want to increase K, so you want to increase the permittivity of the material, and this is nothing but your relative permittivity epsilon r into epsilon naught. So you basically want to increase the permittivity, relative permittivity of the material, and that is also in industry, they also do use this trick to improve the drain current. And this is why people use a high K dielectric. So your insulator is nothing but a dielectric material, and K, what is K is also the same as your relative permittivity. So you want to increase the relative permittivity or the dielectric constant of the material so that you can increase the drain current. Okay, so this is a small K. And there are so silicon dioxide actually works really well in this sense because it has a high dielectric constant. So there are other alternatives as well. So one famous one is this hafnium oxide. So this is in semiconductor industry, people also are talking about like replacing silicon dioxide with hafnium oxide. So in many other, so if it is not a silicon based MOSFET, so if you are using gallium arsenide or any other material as a MOSFET device, so in that case, instead of using silicon dioxide, one can use hafnium oxide as well. Okay, so it also has a very good dielectric constant. So one can also try many other oxides, but this is again, we will not really go into those details. So I want to highlight that how material properties can affect the drain current in this transistor, and what one can vary or tune so that you can obtain a better performance for your device. So one is epsilon, so you can change the oxide thickness, so you can make it very thin. Even you can go below 100 nanometer, but then the challenge is in the fabrication process. You can also change the dielectric material where you have the increase the dielectric constant, and that way you can also improve the drain current or increase the drain current. Another parameter is mu E. So let's look at that parameter. So this is mu E. So mu E is the mobility, but it is the effective mobility. It is not the intrinsic mobility. It is not the intrinsic mobility that you see in silicon. So this mobility depends on what is the electric field that is applied across the insulator and your metal insulator junction. So this is your electric field dependence. So that's why it's known as effective mobility, because you have an electric field. So you have, when you look at the device, so let's look at here. So you have an electric field in this direction. You also have a electric field in this direction as well, because you are applying a voltage from source to drain. So you have two kinds of electric fields you are applying, okay? And there will be a resultant electric field that electrons will experience, and that will determine the mobility of the electron. So that's why we're calling it an effective mobility. It is not really the intrinsic mobility of the material. Now this parameter also one can tune, and this is where we come to the two-dimensional materials. Okay, so this effective mobility you cannot really change or increase that much in silicon. So silicon, already we discussed that silicon has a moderate electron mobility. So that is actually a kind of limits that how far we can go in terms of the transistor performance. So if we keep on making our device better, so we need a material where the mobility is higher. So that's why people are now looking at this 2D materials, where your effective mobility, so mu E or mu H, can be mu H is much greater than your mu E, mu H of silicon. So compared to silicon, these 2D materials have much higher electron mobility or hole mobility, and that's why they can be very good candidate for this channel region, particularly for the channel where your electron, where you want to make sure that electron flows from the source to drain. So you don't change your source and drain, but you want to change the channel material with a higher electron mobility. So this is where this 2D materials actually the concept is really helpful, or probably they can revolutionize the future of your MOSFET devices. So here this is a schematic picture of that. So what you have is a substrate, then you have source, drain, gate, your oxide layer, and what you want is you change the channel underneath the oxide layer using a 2D material. Here this is a graphene. So this is a 2D material with a very high electron mobility. So 100 times more than that of silicon. But again, the challenge is again about the fabrication process, how you can get so graphene is basically this 2D materials are almost like really one atomic layer thick material. Okay, it is not like you can handle with your hands and you can see it in your eyes. Okay, so it is very difficult to incorporate this channel material within this existing semiconductor fabrication technology. But they and research, of course, is going on in that direction, and hopefully in next 5 to 10 years we will have. So there are already devices based on these 2D materials, but not really in a large scale like in markets that you see. But most likely in future we will have these kind of 2D materials in our transistors. So there are many possible candidates 2D materials are there. So graphene is like one of the most famous one, which is basically nothing but a one layer of graphite. So you have a graphite and just take a one layer of graphene or one layer out of it. So that is basically your graphene. So in graphene, your carbon atoms are sp2 hybridized. So it is not sp3 hybridization like in diamond, but the graphene layer that it's a two-dimensional bond that you have is a sp2 hybridized orbital. I think we will not discuss so much about all this 2D. So this is like a flavor I want to give how 2D materials can be useful in future for this MOSFET, this transistor devices. So you have many such candidates, and people are now, this number of 2D materials is actually growing. And people are actually finding out, discovering, or even inventing new 2D materials which are typically thought of may not exist. So you have boron nitride, you have something like MOS2, like typical, these are like transition metal, dichalcogenides. So you have one layer thick phosphorus, one phosphorine. So silicon also one can produce one-dimensional silicon, so it is known as silicene. So similarly from germanium, you have germanin. So from tin, this is tannin. So there are many possible 2D materials that are now being invented in the lab, which typically you cannot produce naturally. Okay? And they are all probably potential candidates for these transistors, and we will see which one will dominate in future. So if you look at their properties, so one property is like if we compare the band gap, so what you see is most of them, so you can have a 2D material which is insulator. This is a boron nitride. So it depends, so it can be insulator, it can be semiconductor, it can be metallic, or it can be even superconductor. So the 2D materials actually, they can behave almost like in three-dimensional materials in terms of their band gap and their electrical properties. Okay, and that's why they are interesting. And in future, we will see more and more of these materials being used in many of the devices. So basic challenge is to look at what is their crystal structure and what kind of bonding is there, and then most interesting part will be their electronic properties. So band gap, conductivity, mobility, and so on. Okay. So of course, one aspect, I mean, there are many facets to this 2D material. So they have really good thermal conductivity. They can have also good mechanical properties. So different applications might use these properties of 2D materials. But from a transistor point of view, what we want is it should have a moderate band gap similar to silicon. Then we should look at the conductivity and the mobility, and also ease of fabrication. So silicon is still dominating because of the large scale technology that is used in the fabrication process, the ease of fabrication that has been established for last 50 years. And to replace that with something which is new and still competing with the silicon, the cost and the performance of this ICs, so that is a challenge for future. Okay, I'll stop here. Any question? So I did not really discuss how this inversion that we saw, the channel forms in the metal oxide layer. So you can read about it, is quite easy. So if you read a little bit in the CASUP, so you'll understand that it is basically, we are assuming it is like a capacitor. So if you assume it is a capacitor and see how the electric field, what is the role of electric field and so when you are increasing the voltage, basically the gate voltage, so what we are doing is applying an electric field across the layer. So the electric field is given by your V, the voltage that you are applying, divided by the thickness, V by D. So the electric field will decide how this inversion or this N channel appears. So if you look at it just simple like a capacitor, MOS capacitor, you will understand that. Very easy if you read in the CASAP book. Okay, any other question? So on 12th, you have the exam. Okay, so I think the Office of Academics will convey to you. The exam will be on 12th. Okay, so thank you then. Exam pattern I'll announce. Okay. Thank you.